season like this, schools will cancel early, and then they'll be more conservative, less conservative, I don't know what to say, but then later on in the season when they should cancel, they don't cancel. So, I don't know. But the thing about my class is I commute from Burlington, so just make sure you watch your email and stuff. If they don't cancel, then I still can take a personal day. So. And you guys shouldn't risk your lives to get here either, unless it's test day. No, I'm just kidding, not even on test day. Okay, so part 3. I brought the globe here today, my broken globe, to kind of get a sense a little bit for scale. The Earth's atmosphere is very thin. The Earth's atmosphere is very thin. This is to kind of try to show you, of course the moon's not in the Earth's atmosphere, okay, but try to kind of show you the little bit of a globe, the Earth's atmosphere. So the Earth's atmosphere is mostly gases, okay, and the reason the gases stay part of our planet is because of gravity. Gravity holds the gases in place. Now notice it's not just gases, but we actually have liquid and solid particles that are floating around. When we talked about the formation of cloud particles, they said that they need to form around an aerosol or particles, so that means we must have particulates. Man-made particulates, and we call it anthropogenic particulates, and just nature particulates. So I mentioned kind of how thin it is. It's kind of we call tenuous, okay? But gravity is pretty good, so it's holding it there. About 60 miles thick, and the Earth's diameter is about 8,000 miles. So this is actually a picture from space to show you. To me, I think I'm looking at clouds, and kind of the haze is the Earth's atmosphere. The clouds are only part of the Earth's lowest layer of the Earth's atmosphere, we call the troposphere, and then beyond that we have 3 other layers that we're going to be talking about. So as we're walking around this room, and actually it's probably going to be a multiple choice question on the Unit 2 exam probably, is when we breathe in air, of course our bodies need oxygen, but most of the gas in the air that we're breathing is nitrogen. It's about 80-20, so nitrogen, oxygen. We use the word aerosols. So in the Earth's atmosphere, we have gases held by gravity, and we have aerosols held by gravity. And aerosols then kind of go with liquid and solid particles that are in the Earth's atmosphere. Kind of an icky feeling. You're like, ooh, we got particles? Yes, we need particles there. We can look at the gases in the Earth's atmosphere and break them down as to either permanent or it's variable. So the permanent gases, they're constant with regard to their concentration. Relatively constant is the word there. The variable gases will vary by location and time. And you know one of these variable gases very near and dear to your heart. We talked about humidity in Thursday's lab. So humidity was water vapor in the air. And that varies a lot, okay? So what else varies? What other variable gases do we have? We'll be talking more about carbon dioxide. It actually varies by location and time. Kind of an interesting cycle. Of course, carbon dioxide is the one that we're concerned about warming our planet. And then ozone actually is, ozone is found in 2 layers of the Earth's atmosphere. We're concerned about if you've ever lived in a big city, sometimes they have ozone alerts, and so that's bad ozone. But the good ozone actually is an upper layer of the Earth's atmosphere, and the good ozone protects us from ultraviolet radiation. So my thing is take some of that bad ozone and pipe it up to where we need it. No one's ever moved on that. Okay, so water vapor can vary from 0 to 4%. If the air is really dry, low humidity, 0%. And remember, there's 2 ways of talking about humidity. There's the absolute humidity and there's the relative humidity. But generally speaking, we say if the air is humid, it has a lot of water vapor in it. Carbon dioxide is the next word. Carbon dioxide. The reason it's listed here is it's variable. We have 3 variable gases listed here. I'm going to show you a graph where carbon dioxide, it's seasonal, actually. It's related to plants. And if you think about carbon dioxide plants, you're like, I think there's a connection. You're right, because plants take in carbon dioxide and then release oxygen. And then this last one here is ozone. So we have good ozone and we have bad ozone. I forgot about this. That good ozone in the upper layer that protects us from ultraviolet radiation, actually it's seasonal too. A little bit about that. One of the things I want to talk about is this phenomenon of our blue skies. I think I see the sun, so it must be if we could look up and see the solar disk around the solar disk, we would see it blue. Now, when it becomes nighttime, I did see the moon the other day, but it wasn't a really good night. Our telescope's out.
Did you see it last night?
No.
Last night was good.
Was it good? Was it pretty?
It was a full moon.
Cool. So when you look at the moon, you don't see blue skies, you see black skies. Okay? And it has to do with the sunlight and the gases in the Earth's atmosphere. So the thing about the Earth's atmosphere is, I said it's mostly nitrogen, 80-20, and then followed by oxygen. And those particles, those gases, in the Earth's atmosphere scatter light. And so this figure right here is kind of showing you the scatter. So here's a shaft of light coming from the sun that's high up in the sky, maybe noon. And you can kind of see the scattering of the short wavelengths of light. I think we kind of just rushed through a little bit about how light has different wavelengths. But if we go Roy, G, Viv, where this is the longest wavelength, and the symbol for wavelength is this, and this is the shortest wavelength. And due to their wavelengths or their energies, they interact differently with matter. So we actually have these short wavelengths being scattered and these long wavelengths coming through. Okay. Now here's the deal. If you are on the moon, and the moon during the daytime, and let's just say you're noon on the moon, okay, you don't have the Earth's atmosphere to do this scattering. So if you're noon on the moon looking at the sun, you're not going to see that a blue sky. You're just going to see the sun. I just think that's pretty cool. Now, of course, we are familiar with kind of this, and it's on the next slide too. But the difference between this sun and this sun, okay, is this sun is noon, and this sun could be sunrise or sunset. It's what we call low on the horizon. It's kind of near the horizon. And the way it works out is, I hope this Earth isn't drawn to scale because he's pretty big compared to the where he's standing on the continent. But the sun's light has to travel through more of the Earth's atmosphere. So here we have the scattering. Okay, scattering, scattering, scattering. In fact, we have so much scattering that it basically removes these colors. So what color do we get to see then? Make it to our eyes? The long wavelengths, the red, orange, and yellow. It's kind of fun in the summertime, here before we know it, hopefully. If you're driving around at sunrise, the sun's low on the horizon. If you look at a stop sign or look at a speed sign, something that's white, a speed sign, you can actually see it kind of glows orange or something like that. That's because the short wavelengths have been removed. And so this slide kind of talks about that too. The same scattering that causes our blue skies is the one that makes the sun so colorful when it's on the horizon. I'll let you find all those words. So, one of the things around harvest time, around here, and I must have read this too, but it makes sense. If we have more particulates in the atmosphere, in the air, than usual, like we have at harvest time, it can actually kind of put a kind of cool twist on our sunsets and our sunrises. Okay, and by the way, I haven't said it yet, but it's on the slide. So if I'm looking for a vocab word, Rayleigh scattering. Rayleigh scattering is what we've been talking about here. Okay. So we already talked about the variable gas water a little bit. Hydrological cycle and all that. Precipitation, evaporation, condensation. But this is now the variable gas carbon dioxide. And I'm going to take you out to the latest data coming up. Historically, I don't know why, they chose maybe somebody like, I don't know, but they chose one of the Hawaiian Islands, an observatory there, I think, and they have been measuring the carbon dioxide content of the air like for a long time. 1960, okay, this is measuring carbon dioxide content. This is years, and then along the y-axis we have carbon dioxide content. I can remember the year that it finally, the carbon dioxide got in the units of concentration or parts per million. I can remember when it reached 400 parts per million. I just checked today, and it's like about 416 parts per million. You might be like, oh, well, that's just Hawaii. What does that mean about the carbon dioxide content in our air? Well, one of the things about air is it gets around. Okay, so if it's happening here, we can kind of extrapolate that to everywhere. But you see kind of the squiggles. So each squiggle, you see two trends hopefully. The squiggles is a year. And then the upward thing is the thing of concern. So the squiggle actually is related to, it's a seasonal change related to plant activity. This says the first part of spring, plants come out, and that's going to happen soon. According to the groundhog, right? No. First part of spring, the plants have been sleeping, and there's lots of carbon dioxide. So actually in spring, when you're like, oh, the plants are coming out, why is there so much carbon dioxide? Because no plants can use it. Well, they've been dormant. So there's actually, there's a peak there. Okay, and then fall time, unfortunately, I like spring and fall. Fall time, you figure the plants have been doing their thing all spring and summer long. So what they do is they are a sink for carbon dioxide, so they have removed carbon dioxide. So actually we have a minimum there about fall. So what you're looking at with regard to the squiggle, if this is time, we have the peak and we have the less. And this is all about carbon dioxide. So this would be spring and this would be fall. CO2 content. All right. The year-to-year trend, okay, is the thing that's concerning. And I have a slide to kind of show you, or a slide and a little video to watch to try to talk about how carbon dioxide makes our planet warmer. But yeah, that's what's concerning. So what adds to carbon dioxide in our atmosphere? Honestly, there are some very natural things. Forest fires, they don't have to be man-made, although it's very sad when they are man-made, but forest fires are a natural thing. And so they actually increase carbon dioxide in two ways. Anytime you burn anything, you put carbon dioxide in the air. And the other thing about forest fires is they remove the sinks for carbon dioxide. So human activities there are natural reasons why carbon dioxide can increase and has increased, but these are the human activities of just burning. Okay, have like the slash and burn sort of mentality for some crops. Burning of fossil fuels when we go to run our cars. Okay, that's actually anytime you burn anything, including the combustion that happens inside of our cars, we're putting carbon dioxide into the atmosphere. Deforestation, we're removing what we call the sink, CO2 sink. So this is actually then the latest data. Sometimes it's called the hockey stick diagram. A more fancy word is the kneeling curve, Keeling, not kneeling, Keeling curve. Okay, so here we go. This is 1 week, and this is that place in Hawaii that's measuring the carbon dioxide content. I know a few years ago, maybe a year ago, I don't know, but it was actually potentially on the chopping block as a place that we needed to save money and why we needed to have this research going on. But anyway, it survived that cut. So that's 1 week. And then I'm just going to kind of hover. This is 1 month. Maybe. There we go. That's 1 month. See more data points, the black of the data points. Anytime you gather data and put them on a curve like this, you're going to kind of see some, it looks a little noisy to me. But I mentioned the going over the 400 parts per million threshold. We're at 412 now. Okay. 6 months. Start to see something. This is a good one. 1 year. 1 year you start to kind of see this, which makes sense. We have our peak CO2 in the spring and our minimum CO2 in the fall. 2 years. 2 humps. Okay. Can barely maybe start to see a trend. This is a good example of you really, sometimes some things in life, some things in science, you need to be able to look at it for a long period of time. And that's why this, since 1960, has been a good thing. This is the full record that actually kind of like we have on in our textbook. Okay. So our textbook was a little dated. It stopped at some point. You can see the yearly, the spring and the fall, spring, fall, spring, fall, spring, fall, but kind of an increasing. So that is, that's from Hawaii. I'm going to take you out. I have 3 more ones to show you. 1700 to present. Okay, so this wouldn't be just from Hawaii. This would be all sorts of different ways of getting this information. This information, for instance, we can actually get it from, is this right? Yeah, we can actually get this from, I want to say tree growth. Okay. So now we kind of lose the bumps because it's we're looking at more years. But we can start to kind of see this problem right here. So I'm bad at history, but at some point, the Industrial Revolution, we started using fossil fuels. Actually, probably starting with coal and then on to oils and gas. Okay, this is actually kind of the Industrial Revolution. Early 1900s? Okay, so you might be like, how can you get 10,000 years? The next 2 graphs I'm going to show you, I know one of the ways to get carbon dioxide content way back then are ice cores. I don't know if you've seen the movie, it's kind of an old movie now, The Day After Tomorrow. The opening scene is where they have these ice cores. And what they do is it's been undisturbed, and the cool thing about the ice sheets up here is it's been layered. This is an old layer and this is a new layer. So if you're careful about it, you can actually get the core and bring it back to the lab and slice it and understand what was going on back then. So this was actually even more exaggerated then. Okay. So this looks like the hockey stick that we're concerned about. Okay. Now, the last one I'm going to show you probably must be ice core dated too. It looks a little more noisy because you'll hear people, you can see that this is carbon dioxide content. So you can see it's gone up, it's gone down, it's gone up, it's gone down, you know, up, down, okay? But it's never been that. So sometimes people will say, the surface temperatures, the temperatures of the Earth's atmosphere, it's gone up, it's gone down, it's gone up, it's gone down, it's gone up, it's down, it's gone down. But since humans have been in the mix, we're concerned about a trend that we see now that is outside of what we saw before humans were there. So this is kind of where that's all coming from. All right, that's a happy day, isn't it? So I'm going to show you a video about global warming. Okay, but kind of at the crux of, to me, global warming is very similar to if you have your car parked. Let's go back to a summer day. Let's go back to a sunny summer day, and your car is parked, and you have black interior in the car that you really enjoy. Like my car has black interior. Okay, and you guys told me the other day that black actually you'll get hot. So what will happen is the sunlight will come through our window. It will interact with our upholstery, black upholstery, and then it will heat up. And then the thing about our windows is they allow short wave in, but they don't allow long wave out. Okay, so here's the deal. The Roy G. Biv, I'll take the color red. A little bit longer than infrared, or sorry, a little bit longer than red is infrared. And infrared is heat. So what this is saying is these guys come in, they interact with your upholstery, they turn that into heat, and your heat can't go out. That's kind of like, it's the same principle for a greenhouse, like little plants and such. Okay, so visible sunlight penetrates through the atmosphere. So, and it warms. Okay, so what does this have to do with? I didn't link it. That's your car. How does that link to carbon dioxide? Here, I'll go ahead and do this. Now this, I'm switching gears. This is no longer my car. This is my Earth's surface, and this is the Earth's atmosphere. And then I'll go ahead and draw in some particles. This is, I think, what you're going to see on the animation. Those particles, I know they're not present in a great amount, but those are my carbon dioxide particles. So, kind of like the pane of glass, what can happen then is those particles allow short wavelength to come in, okay? And then that will warm the Earth. And then this actually is my heat coming off the Earth. And those same particles block or interact with long wavelength. They block infrared. So that's kind of what it is. So let's see. Without further ado, it made us think that, man, I am so glad we have some greenhouse effect. Otherwise, we'd be like the moon. But it's the kind of the runaway or enhanced greenhouse effect that we're concerned about as we increase carbon dioxide in the atmosphere. It also showed us that it's not only carbon dioxide, but it's also methane, which actually has been in the news recently because cows are notorious for having 7 stomachs, I don't know, and they do the whole methane thing, cow farts. So methane is actually something that will warm our atmosphere, as well as water vapor. Water vapor is another greenhouse gas. Okay, so a little more nuts and bolts. I'm going to ask you in some form the layers of the Earth's atmosphere, and this is from the closest outward, so it's kind of backwards. I know this is the top, but it's really this is the closest. So we have the troposphere, and actually that's where most of our weather occurs. Do this. So it's funny, as I'm going to draw these layers on the board, they're really, like I said earlier, really pretty thin compared to the diameter of the Earth. So here we have the troposphere, and we're going to see that it is the thinnest. And when we talk about severe weather, which we will get to, the tropopause is kind of this little layer right here. And the word pause means lid, I think. And so the troposphere has a tropopause on top. I mentioned that about severe weather because we actually, even though the troposphere contain, I'll draw a cumulus cloud, contain most of our weather, if we have thunderstorms, actually they go past the tropopause and they create these what's called overshooting tops in an anvil. So that's my thunderstorm cloud. All right, what else do we have? The stratosphere. I'm going to show you here in a minute this Red Bull jump, which I would not like to be that dude's mother, but how he actually took a balloon up into this region and fell through and landed successfully. So the good ozone is in the stratosphere, and the stratosphere is thicker. They get thicker and thicker. And one of the things, it's coming up here in a minute. And also in the stratosphere we have our ozone layer. Then we have the mesosphere and the thermosphere. They keep getting bigger and bigger, and I kind of running out of room here. So stratosphere, meso meaning middle. I don't have a lot to say about the mesosphere. The thermosphere, and I have one more layer to talk about, but the thermosphere actually is where you figure at some point it's going to peter into outer space, because this is the Earth's surface, and those are the 4 layers of the Earth's atmosphere. Okay, let's take a look at this Red Bull video. So there's 4 main layers of the Earth's atmospheres. There's other ways to chunk it up. Actually, there's what's called an ionosphere, and we haven't done the chemistry unit, but they actually touched on the video we watched that an ion is just a charged particle. And the thing about the ionosphere, where it's the upper part of the mesosphere and then into the thermosphere, so it's like this. Ionosphere. The thing about that is that's where charged particles from the sun can hang out, and they usually hang out and just they don't do much. They're kind of trapped by the magnetic field around the Earth. But if it gets too many charged particles from the sun, what will happen on my globe? But what will happen is in the polar region, we'll actually have charged particles eking down. Okay, our magnetic poles, and that creates our northern lights. Okay, so it's kind of a sun thing. Oh, northern lights or southern lights. Okay. So ozone, I said we have good ozone and bad ozone. But the formula, like just the formula for water is like H2O, 2 hydrogens, 1 oxygen. The formula for ozone is O3, so it must have 3 oxygen particles, and that's what it does. So basically then, our good ozone, we said, was actually located here in the stratosphere. That's where our good ozone is. And we're concerned about its depletion. We're concerned about the good ozone going away. And the ozone layer is kind of right here. You probably heard about the ozone hole, and I'm here to and it has ramifications. The ozone hole is real, and it actually is created over the poles seasonally. Okay. What has depleted our ozone? The good ozone. So this is ozone. This is good ozone. Is actually chlorofluorocarbons is one of the most culprit, and we've curbed the use of chlorofluorocarbons since I want to say 1980 or so, but it takes a long time for the atmosphere to heal. So the good ozone actually blocks incoming ultraviolet radiation, and that's why it's so important. The bad ozone, and I mentioned if you live in a big city, sometimes you'll have these ozone alerts. And the bad ozone is here in the troposphere, and it's related to actually pollution. So this last bullet, this third bullet, goes back to actually the good ozone and the ozone hole. What you're looking at there are 2 images of looking down at the pole of the Earth. So this is, they're both, let me say, the northern hemisphere. This is in 1979, and this is in 2010. And the blue actually is the depleted ozone. So again, it's local, okay? But, yeah. And this kind of talks you through, ozone hole is the word. This won't make it to the test, but it kind of talks about why is it seasonal, and there's this one more, we talked about 10 cloud types, there's one more, well, at least one more type of cloud called a polar stratospheric cloud. Polar meaning poles, stratospheric meaning it's in the stratosphere, not the troposphere, so it's a weird sort of cloud. And what happens then is when the clouds are present, they tie up the CFCs, and as the cloud starts to break apart, like in springtime in that hemisphere, then the CFCs are kind of loose all at once to attack the ozone in the stratosphere. So that's how that works. Okay. So one of the things, when I'm looking for things to say about these 4 layers, this is one of the things that you can say. As you're going up in the troposphere, it gets cooler. And actually, I mentioned this the other day when we talked about different types of precipitation. So as you go up, it gets cooler. Okay, if you climb a mountain, you know it's going to get cooler. Weird thing is, as you go up in the stratosphere, it gets warmer. This is weird, I think. It gets warmer. And actually that warmth I think you could think of it as being related to kind of the ozone layer. Excuse me, it gets warmer. And it alternates, so in this layer it must get cooler, and it does. And in this layer it gets warmer again. But the temperature in the thermosphere is kind of an interesting thing, because you're like, thermosphere? Wait, that's where it peters into outer space. And I kind of like to think in that, it's weird, like at what point do you count our atmosphere as no longer, like it's kind of a density thing? So you're like, oh, if I have one gas particle per, I don't know, square cubic mile, does that mean we're at the edge of our atmosphere? It's kind of weird how it peters out. If you've seen the movie Gravity, I don't know if this is a good example, but I just picture her, she was kind of stranded out there, kind of floating around for a while. And it's almost like I picture the side of her that's facing the sun was all warm and toasty, and the side of her not facing the sun was extremely cold. Temperature is, you need to have particles in order to have a temperature. So anyway. This actually kind of shows you the trend I just said. So along the x-axis you have going up in elevation, along the x-axis you have temperature. So here's how it's getting colder as you go up, getting warmer as you go up, getting colder as you go up, and getting warmer as you go up. It's exactly what I said. Sounds like our thing's getting ready to take off. Well, this is a good place to take a break. So we'll finish this on hopefully Wednesday. Part 4, no, this is kind of part 3. Part 4 is really pretty darn short, so we should be able to knock that out. So nothing due for Wednesday, but maybe 2 things due Friday.